Hi everyone, welcome to the 14th lecture of CS 188. Let's start with a couple of announcements for today. Your midterm was earlier this week, I hope you know. Somebody knows. Solutions have been posted on Piazza. Check them out. If you disagree with any solutions, definitely let us know. Grading is in progress, will hopefully be done pretty soon. Next thing up for you to work on is homework 6, which was just released and will be due on Monday. It'll be, as usual, a homework with 3 parts. There will be a self-assessment of the previous homework, there will be an electronic for part of the homework, and a written part of the homework. Any questions about logistics? Okay, let's start with the technical content then for today. Today will be about basenets. You already had one lecture on basenets where you got to understand what they are, and you had a lecture before that on probability, and we'll be building directly on both of those lectures today. Quick recap. Conditional probability. The conditional probability of X, let's say capital X, taking on value small x, which we shorthand this way. So just as a reminder, this is a shorthand for probability random variable x takes on the value small x, given random variable y took on the value small y. So conditional probability of x given y is the probability of them occurring together divided by the probability of y. So that is saying, whenever y occurs, what fraction of times does x happen? That's the conditional probability of x given y. You can reorganize this, and this gives you the product rule, that the joint probability of x and y is the probability of y times probability of x given y. You can also reorder the variables to get the other version, y given x times px. Then chain rule, which is a generalization of the product rule, and it's a way to write out joint distributions over many variables. The joint probability over all variables, x1 through xn, is the product of the probability of x1, then the conditional of x2 given x1, then x3 given x1 and x2, and so forth. Written in shorthand notation is the product of all conditional probabilities of each variable conditioned on all the preceding variables in your ordering. If you had only 2 variables, n equals 2, it becomes this thing over here. For n equals 2, there was 2 ways of doing this. You start with x or you start with y. When you have n variables, you have n factorial ways of writing out the chain rule. And depending on the problem you're solving, one way of ordering the variables might be more beneficial than another way. Independence. X and y are independent if and only if, for all values of x and y, the joint probability of x and y is equal to the product of the individual probabilities. So that's just a definition of independence. If this is true, then we call these variables independent. There's something called conditional independence, which is going to be true a lot more often, and hence a pretty useful concept in what we're doing. X and y are conditionally independent given z, if and only if, and what will show up here is something that looks exactly like what we had before, but now everywhere there's a conditioning on z. That's the only change. So everywhere we now condition on z, and of course, and it has to be true also for all values of c. Okay. Shorthand notation, x independent of y given z. Basenets. Basenets were a way of encoding joint distributions over many variables in some way that is more efficient to encode a distribution, and also gives us maybe a bit more insight into the structure of the distribution because there's a graph associated with it. For example, here we have a bunch of random variables: age, good student or not, mileage, risk aversion, vehicle here, extra car, senior training, make, model, and so forth. And this graph is sketching out, in some sense, how these variables relate to each other. For example, age might affect driving skill, and age might affect medical cost in case somebody gets in an accident, and so forth. Questions we can ask once we have a basenet encoding a joint distribution are all the questions we can also ask from any joint distribution, because a basenet is just one way of representing a joint distribution. The joint distribution is still there. We can still ask questions about it. So given a fixed basenet, we can ask, what's the probability distribution for x given some evidence variable e? So maybe, what's the probability of high medical cost given a certain student status and yearly mileage of the person you're looking to insure? You can also ask representation questions. Given a basenet graph, what kind of distributions can it encode? That's what we're going to look at a lot today. Like, what kind of assumptions do you really make when you put down a basenet? What do you gain? What do you lose? And then there's a lot of modeling questions in practice is, what basenet is actually a good model for the things that we see in the world? And to do the modeling well, you kind of want to understand what independence assumptions you are making by choosing a particular structure. Okay, so let's recap the semantics of basenets. Semantics of basenets. A basenet is a directed acyclic graph with one node per random variable. That's the graph part. Then in addition, there is a conditional probability table, we call a CPT, for each node. And that table says, what's the probability of this variable given its parent variables? Together, all these conditional probability tables, if you multiply them together, you get the full joint distribution. Okay? So basenets are a way to build full joint distributions by only specifying conditionals given parents in the graph. In practice, that might be a lot more feasible. Specifying a full joint distribution can be very difficult because, just let's say, go back to this graph. Full joint distribution, you want to specify numbers. There's maybe like 24 variables here. Say, okay, for each of those variables taking on a certain value, what is the probability? That's very hard to come up with that number. But if all you need to do is say, given the socioeconomic status, what is the probability this person has an extra car? That's a much easier thing to think about. And so by using a basenet, it might be easier to specify the model by specifying pieces of the model, which you then multiply together to get the full joint distribution. Okay, here's the canonical example that many books use. Whether the variables here, B, burglary, E, earthquake, A, alarm, J, John, and M, Mary, and it encodes a story. The story here is that there could be a burglary, or there could be an earthquake, or there could not be. And as a consequence, your alarm might trigger. But you're not at home. So, and I guess this is back in the days when your alarm wouldn't talk to your phone directly, but you might have neighbors who hear the alarm go off in your house and might then decide to call you and say, hey, your alarm is going. Either John or Mary or both could decide to call you. And then the tables here encode the probabilities of these things happening. For example, when the alarm goes, which is plus A, the alarm is going, John has a probability of 0.9 of calling you, 0.1 of not calling you. For Mary, when the alarm goes, there's a probability of 0.7 of calling you, 0.3 of not calling you. Here's the bigger table. This one encodes the conditional of alarm given burglary and earthquake. Highest probability of alarm. Highest probability of, plus A. Highest probability of alarm going off is 0.95 and happens when both burglary and earthquake are happening. If it's just burglary, already has a high chance of going off. If it's just earthquake, It also already has a pretty high probability of going off, and so forth. And so these numbers might be much easier to specify than a table that has, in this case, 2 to the 5 entries for every possible combination of all variables. If we want to then compute an entry in that table that's hard to specify directly, but we still want to reason about, all we need to do is find the corresponding entries, multiply them together, and that would be the entry in the full joint distribution. Okay, that's the recap. Any questions? Because we're going to be building on this for the rest of the lecture. Okay, so let's start asking some questions about the benefits we get from using base nets. Okay, let's say we have a joint distribution over n Boolean variables. Each variable can take on 2 values. Okay, how big is the table representing this distribution? Well, this table will need an entry for every possible combination of these Boolean variables. How many combinations are there? 2 to the power n. So this table will be of size 2 to the power n. It's a lot of numbers to specify and also difficult numbers to think about. How about a base net with n nodes? So there's still n variables. And each node can have at most k parents. How large is the sum of the sizes of all the tables that we need to represent a base net with this kind of structure? Any thoughts? Over there? The suggestion is n times 2 to the k. What would be the reasoning there? Well, let's think about each individual table, how big it's going to be, and then we can multiply with n to see how big the overall thing's going to be. So one table, how many entries does it need? Well, if a variable has k parents, you need to specify a probability for each possible combination of values of the parents. If there's k parents, there's 2 to the k combinations. So this table will need 2 to the k entries to specify for each of those combinations what is, let's say, the probability of positive for this variable. And then the probability of negative will just be 1 minus that probability. If you explicitly represent the probability of the negative, then you'll have just twice as many entries. So if you explicitly also represent the negative, you have 2 to the k plus 1, 1 entry for each combination of the parents and the variable itself. This is for 1 CPT, and there will be n CPTs, so that's the total size. Look at the difference. Exponential growth tends to be the one that gets you. Linear growth is not too bad. It's often pretty hard to avoid, actually. But the exponential growth gets you in a bad way. Let's say you have, 100 variables. 2 to the 100 is a really large number. But if you just have 100 times 2 to the k, this shows that as long as you keep the number of parents per node small, the storage you need for your base net is relatively small. And so you can already start thinking about this when you design base nets. Often the name of the game will be ensure that not any single variable has a large number of parents. Because if you have any single variable with a large number of parents, that conditional probability table will dominate what you need to do. Both, by the way, whether you have a full table or a base net, allow you to calculate the full joint distribution, but then base net has lots of space savings as long as you don't give any node too many parents. It's much easier to put the numbers in these smaller conditional probability tables than in the full joint tables. And next lecture, we'll see it's also quicker to answer questions of the form, what's the conditional distribution of X given some evidence when you have a base net than we have a full joint table. Okay, so that's a recap of representation. Topic for today will be the next thing here, conditional independences, and then inference will be for next lecture for exact inference, and the lecture after that for approximate inference. And then after that, we'll also start looking at learning the base nets from data. Okay, representation is going to be all about independencies, at least in this lecture. So let's recap those definitions and notation. X and Y are independent if, for all X and Y, the joint is equal to the product of the marginals. This is the notation. X and Y are conditionally independent given Z. This is the notation for that. If the exact same thing holds as above, but now everywhere we condition on Z. only change. In fact, that's true for many, many things in probability. If you have some equality that's true, and then you introduce an extra variable, and you everywhere condition on that extra variable, probably that same equality would still be true. Conditional independence is a property of a distribution. So when somebody gives you a distribution, you can go check. You can check all those conditions and see if they're true. Then you can claim independence or conditional independence. For example, let's say this robot is making a fire in the house, or could not be making a fire in the house. A fire might cause smoke, and then the smoke might cause the alarm to go off. What is the conditional independence we would have here? Well, if we know there is smoke, so we're conditioning on smoke. If we know there is smoke, knowing whether or not there is fire doesn't tell us anything new about whether the alarm will go off or not, because we, in this model of the world, assume the alarm is triggered by smoke, and so once we know there is smoke, it doesn't really matter what caused that smoke. The alarm will be triggered based on that smoke. And so the alarm going off or not is independent of fire, given we already know there is smoke. And by the way, the ordering here doesn't matter up front. You can just as well say fire is independent of alarm given smoke. If it holds one way, it holds the other way, because if you look at the equations here about independence, the roles of x and y are completely symmetric. Okay, so what assumptions do we make when building a Bayes net? If we want to represent any distribution, we can always represent it by applying the chain rule, a product of conditional distributions of the current variable given all preceding variables. What does a Bayes net do differently from just applying the chain rule in the general way? It says instead of conditioning on all past variables, I'm just conditioning on the past variables that are my parents in the graph of the Bayes net. By doing this, if we select a parent set that's smaller than all preceding variables, we have made an assumption. Because if the chain rule always applies, but once we leave out one of the preceding variables, we lose some expressiveness. There are certain distributions we cannot represent anymore. We lost something. We also gained something. We gained that it's easier to write out conditional tables with small number of parents, but we lost something in that some distributions will not be possible to represent by a Bayes net if the parents of a node are not all the previous nodes. Now, this we know that we're doing when we write out the distribution as a product of conditionals, and we only condition on parents, not on all preceding variables who make an assumption. The question we're going to answer today is there anything that we implicitly assume in addition to this, where by assuming this, we're forced to also assume other things that are not already listed in this equation here? And what we'll see is that actually we can often read these things off from the graph. So we will not have to go look at the actual numbers. We can just look at the graph of the Bayes net and draw conclusions about assumptions that are made about the distribution. Of course, that's important once we start building models, because we want to understand what assumptions we built into our models. Let's do an example. So here's a very simple Bayes net, 4 variables, x, y, z, w. In the first bullet point, let's look at the conditional independencies that we have introduced just by going from using the chain rule to using the conditioning on just the parents. So a chain rule would say Px, y, z, w is Px, Py given x, Pz given x, comma y, Pw given x, y, z. That's chain rule. What does the Bayes net say? Bayes net says, I'm okay with instead using still P of x, still P y given x, but then for z, x is not a parent, only y, so we just use z given y, and then for w, only z is a parent. So we drop the x over here, we drop the x and the y over there. Those are assumptions we made by using a Bayes net of this structure and not using the chain rule. What would you do if you didn't want to make those assumptions? Let's say you were not happy with those assumptions. You said, that's not right. I need W conditioned on X, Y, and Z. Well, then you need to introduce more arrows in your basenet. If you want W to be conditioned on X, Y, and Z, then you need to add this arrow, and you need to add this arrow. Once you do that, you get W conditioned on X, Y, and Z. But that's not the basenet we have here. We're just having Z as the parent. Okay, so how do we write that out in terms of conditional independences? We said by doing this one here corresponds to saying Z is independent of X given Y. This one here is saying Z is independent of X and Y. Actually, let me write as capitals. Z is independent of X and Y. It's not Z, wrong one. W. Working with W here. W is independent of X and Y given Z. So these are the two assumptions we made by choosing this graph and by just looking at the chain rule simplified to what the basenet will prescribe. Are there any other independencies than these two that are guaranteed to be true for any distribution of this form factor, not that one, this one here? Any others that are guaranteed to be true? Any thoughts? Let's think about this intuitively. What else might be true? If we look at this graph, it seems like, in this particular case, we have a chain, a causal effect chain. X seems to cause Y, cause Z, cause W. That's what this roughly encodes. So if we know Y, knowing Y takes any influence of X on W away. So another independence we can write is W is independent of X once we know Y. We haven't proven this here, but that's an intuition that we can read off from this graph. And it's the kind of conclusion that today's lecture will be about, that you can generally read off from graphs which independencies are guaranteed to be true, in addition to the ones that the basenet definition already gives you. Okay, so important questions about basenets. Are two nodes independent given certain evidence? If the answer is yes, you can prove it using algebra. There's a definition for independence, so you can work through the algebra and prove it. This can be tedious in general, and so today's lecture will be about avoiding needing to do all this algebra and having a graph algorithm that can tell you the answer. If the answer is no, you can prove it with a counterexample. So you can say, well, this independence is not true because here's an example distribution showing that this independence is not true, and the example distribution can be represented by the basenet that you just gave me. For example, here is a basenet. We can ask the question, are X and Z guaranteed to be independent? Who thinks X and Z are guaranteed to be independent? Who thinks they're not? Okay, why not?
Well, they're connected through Y.
So they're connected through Y. That's why the thinking is, well, they're not guaranteed to be independent. So what can you do? You can say, I have this reasoning. X can influence Z because this story over here is one way to explain it. Maybe there's low pressure, which causes rain, which causes traffic. And I can associate a distribution with this. I can actually put numbers down and say probability of Y given X maybe is Y is always equal to X. Z is always equal to Y. And if that's the case, then we know that X influences Z and they're not independent. And to show that there is no independence, just one example is enough. If we did want to show independence, we'd have to show it to be true no matter what numbers you put in the conditional probability tables, which is what we'll do most of this lecture. One question, is it possible, if somebody gives you a basenet like this, that X and Z are actually independent? Who thinks that's possible? Why?
The only condition for independence is if you take like the individual probability
Mhm.
condition and independent, then we could say they're
Okay, that's the right kind of reasoning. Now to complete it, so the reasoning was, if somehow the product works out that things are independent, then we still achieve independence, even if this is the graph structure. And now a question is, can we come up with a conditional probability table for x, y, and z, such that indeed there will be independence? This is kind of a little bit of a tricky thing, because it's very counterintuitive, because why would you use a basenet like this if x and z are independent? But the question here is, mathematically speaking, could we still make them independent? And the answer is yes. You just make x a coin flip, 50-50. You make y a coin flip, 50-50, independent of the value of x, and same for z. Now, everything is independent coin flips, but you can still represent it with this kind of basenet. It's just not very smart to use this basenet to represent that distribution, because this basenet is overkill for a distribution over all independent variables, but you could do it. Just every table in the CPT, every entry in every CPT will be 1/2. And that's it. Okay, let's start thinking about how we can come up with graph algorithms to conclude independencies between variables in basenets. The way we'll do is we'll first study this for triplets, and then for more complex cases, we'll refer back to the triplet cases and say, okay, this complex case can be solved by just looking at triplets that constitute the more complex case. And the thing we'll come up with ultimately is something called deseparation. Okay, here's one triplet. X points to Y, points to Z. For example, low pressure could or could not cause rain, could or could not cause traffic. This is the distribution that we get when using the above basenet structure. First question, can we guarantee X independent of Z? We just talked about that. We cannot guarantee that. It was on the previous slide. Answer is no, because X could influence Z in this kind of basenet. How do we show this? Well, we can show it by thinking through a story, but even more concretely, to mathematically show it, we can come up with some numbers. We can say, here's a story, let's now put it in numbers. Y is always equals to X, Z is always equal to Y, and then let's say X is 50-50, then there is clearly an influence from X onto Z, and we cannot claim independence. So if somebody asks you, given a distribution represented with this basenet, but I did not give you the numbers in the CPTs, I just gave you the graph of the basenet, can you claim independence of X and Z? The answer is no. How about, can we guarantee X is independent of Z given Y? Intuitively, yes. That's the whole intuition of this kind of causal chain, is that one causes the next, and if you know the one in the middle, it doesn't matter anymore what the one before it was. So our tentative answer is yes, X is independent of Z given Y. And again, to make this question very explicit, the question is, if somebody tells you this is the structure of the basenet, but it's not giving you any conditional probability tables, it's just saying this is the structure, that's all you know, without knowing the tables, can you conclude that X is independent of Z given Y? And we're saying yes, and we're going to prove it. So let's write it out. Conditional of Z given X and Y, by definition, is equal to the joint of X, Y, and Z divided by the joint of just X and Y. Now for each of those, we can fill in how they are represented in the basenet. The joint of X, Y, and Z is the product of what's shown on top there, and the joint of X and Y is the product of what's shown at the bottom. Now we can simplify. What we're left with is just Z given Y. So what we have here is the conditional of Z given X and Y equals the conditional of Z given Y, which means Z is independent of X given Y. And what it shows is that if we have evidence along such a chain, it blocks the influence from the early variables onto the later variables. Now, just to be very explicit about where did the basenet come in? Where did we use the fact that we have this specific basenet, and why and that we can reach this particular conclusion, it happens in this step over here. So when we go from here to here, in general, when we apply the chain rule, we can't just write z given y here. We have to write z given x and y. But because of this base net structure, it assumes we can write the probability distribution this way. That's where the assumption comes in. Next, we can simplify and reach our conclusion of conditional independence. Okay, let's do another one. Common cause. So maybe a project could be due or not. Then based on whether a project is due or not, forums could be busy or not, and labs could be full or not. So we have one node at the top, which might cause two separate effects. This would be the joint distribution encoded by this model shown here. We call this common cause because there's two effects that are caused by a single thing. Is there guaranteed to be x independent of z? Answer is no. Why not? Intuitively speaking, when projects are due, it's more likely that both the forums are busy and the labs are full. And when there's no project due, it's more likely that they're both not busy and not full. So clearly, x and z are correlated. They're not independent. They tend to be on and off more commonly together than not together. So that means they're not independent. So all we need to do to show this is not guaranteed, if somebody gives you a basenet, just a structure, not the CPTs, and asks you, is there an independence? You say no. All you need to do to prove that no is to say, here is a conditional probability table that has it not be true. So for example, this is the story we just told, and in numbers, we make x take the same value as y, we make z take on the same value as y, and if that's the case, then x and z will take on the same values, and clearly they're not independent then. So it's an example of a choice of conditional probability tables that shows just proclaiming this structure of your basenet is not enough to be able to conclude anything about independence of x and z. In fact, generally it won't be true. How about if we condition on y, the node in the middle, are x and z conditionally independent given y? Okay, intuitively, yes, because that's the common cause, and once you know the cause for z, it doesn't matter what x is doing, because it's y that's causing z. We can now again go through the math. We have, what is the conditional of z given x and y? We write it out, same definition as before. Next step, we're going to use the structure of the basenet to fill in this specific instantiation of the of the joint distributions for top and bottom. Again, assumptions have been made. The last variable here, z, is only conditioning on y. If you apply the chain rule, it would have to condition on x and y, just y. That's the basenet assumption for this basenet structure. After we do that, things simplify, and we're left with just z given y, which shows that z is independent of x given y. Because once we know y, adding in x in the conditioning does not change what we know about z. Okay, so observing the cause blocks the influence. Here's another one, third type of structure. With three variables, there's only so many things we can do. This is the third type of structure that's available to us, where they have two variables that point into the bottom one. For example, the story could be, it could rain or not. There could be a baseball game or not. And then, as a consequence, there could be traffic or not. Are x and y independent in this kind of basenet? So again, what does that mean? If I ask the question, are x and y independent in this kind of basenet, that means that no matter what choice of conditional probability tables you associate with each of those variables, the joint distribution should exhibit the fact that x and y are independent. Who thinks yes? Somebody there, red shirt? You want to explain why? So the intuition here is x and y are drawn independently. There's nothing causing them to be correlated, and so we expect independence between them. What do we need to do to prove this? We'll have again to do the math that we've been doing all along. Not doing it on this slide here, but it's the same kind of math that we did on previous slides, where you would write out, using that this distribution is of the form px times py times z given x comma y. And by using that structure, you'll be able to show that the joint of x and y equals just px times py. Are x and y independent given z? So once you know z, once you know there is traffic, is there now any influence between x and y, or are they still independent? Who thinks they are now not independent anymore? Why?
Because we know there's traffic. Maybe the high chance that's more favorable as so it's not.
Okay, so the intuition here, the intuition is correct, and I'm just going to rephrase it because it's hard for everybody to hear you. Intuition here is that imagine you know there is traffic, and you're wondering, would there be rain, would there be a ball game? You're not so sure, but because there's traffic, you say, well, my probability for both has gone up. Because there's traffic, and either one could have caused that traffic. So higher probability of rain, higher probability of ball game. Then somebody tells you there is a ball game. At that point, your probability for rain will drop. Because there was two possible causes of traffic. Initially, you didn't know which one might be the one, and so the probability for both went up. But then all of a sudden you know there is a ball game, so that's enough explanation for there being traffic, and that now decreases the probability of the other explanation. All right, so whenever there is multiple possible explanations, that's the scenario here. There's multiple possible explanations for something to happen. When that thing happens, probability of all of them goes up, but then when somebody tells you one of them is true, that'll drop the probability of the others. Okay, so that's the story here, and you can actually then write out a probability distribution that has exactly this story encoded in it, and then if you check the condition for independence of x and y given z, you'll see the condition doesn't hold true, which is proof that we cannot claim this. Okay, now let's look at the general case. What have we seen so far? Or what do we want to do now? We want to now, for any basenet, figure out whether two variables are independent given some evidence. We want to do it by just looking at the graph, not looking at the conditional probability tables and do some tedious work there. And we'll do it by breaking it down into the canonical cases we already covered. So, let's take a first pass at this. Let's say you're given a basenet, and somebody asks something about, are these two variables independent given the other variables? You might say, well, let's just check if there's a path between the variables, and then do something with that path. And a naive thing could be, I'm going to shade, to make it easier to think about this, I'm going to shade evidence nodes. So if we observe, let's say, R, we will shade R, and then maybe we might ask, is L independent of B given R? Might be a question. Like, L independent of B given R could be a question we ask. And then we could say, well, maybe all we need to do is look at the path between L and B, and there's a shaded node in between which might block the influence, and we're all good to go. Turns out it's a little more complex than that, because we've seen in the triple suite just analyzed that if the shading happens in one of those bottom nodes, it actually activates the influence rather than deactivate the influence. So we need to be a little more careful. So let's spell this out explicitly. So whenever we have a path, we're going to break it up into triples. These triples are going to be overlapping triples that together make up an entire path. And if we ask the question, are x and y conditionally independent given some evidence variables z, we will check paths between x and y and check every triple along that path and check for each triple if it's active or inactive. With the work we already did, we know that these are the active triples and these are the inactive ones. Okay, we actually did not do the work for the bottom one here, so let's do a little bit of explanation about this one. What's this one here? This one is saying if I have a common effect where there's multiple things that could cause something, it's not just the case that influence can travel in this scenario here, but the evidence that we observe can also be much further down, and that'll still trigger influence between the variables. It's like if we go back to the example we had here, we had traffic, but what if we, from traffic, hang off another node, maybe accident has been reported or not? Then it's also going to be the case, initially you observe nothing, then you observe there has been an accident. The accident having been there makes you think probably there is more traffic, probably there is rain or ball game. This model would assume the more traffic, the more likely there's an accident. And just knowing there's an accident will already cause influence between these two variables up here. So that's the bottom one here, and then we have the inactives on the right. So to draw any conclusions, we'll break it up into those, and we just need to remember which one falls onto which side. Any triple, and you'll want to be able to recognize that easily. Just remember, essentially, typically when a node is shaded, it'll block the path, but the exception is when it's one of those V structures where it'll actually activate the path rather than block it. So that's the triple categorization. Now we'll get a query. Are two variables xi and xj independent given some evidence variables? Okay, we'll check all undirected paths between xi and xj. We check a path. For every path we check. And if one of these paths is active, then independence is not guaranteed. Because once there is an active path, some influence can flow, and that's it. There is no independence. If you have checked all paths, and by the time you checked all paths, you have not found any active paths, so they're all inactive, only then can you conclude there is independence, because there's not a single path that can influence one variable from the other one. Okay, let's take a short break here, and after the break, let's work through a few examples of how this works. All right, let's restart. Any questions about the first half of lecture? Yes?
Why is it necessary to look for all conditional independencies among your basenet?
So the question is, why is it necessary or maybe interesting to look at all the conditional independencies in your basenet? The answer is that when you want to model a joint distribution over many random variables, to do that, A BaseNet can help you express that distribution by not requiring you to write out a full joint distribution, which is extremely large to write out and difficult to come up with the numbers. So it's nice. The BaseNet helps you with that. But then when you choose a certain BaseNet structure, you're making assumptions. And so the reason is to understand what assumptions you are making depending on how you structure your BaseNet, such that you don't make assumptions that maybe you realize are actually faulty assumptions and will limit what you can do with the model that you come up with, because the BaseNet graph is already constraining you and not allowing you to represent maybe effects that you know are there, but that you now made impossible to represent because you introduced some independencies. Okay, let's do an example. First one, is R independent of B? How do we do this? What's the procedure? First step, we try to find all paths that connect R and B. It's only one path. This is the path. Along that one path, we check all the triples and check whether they're active or inactive. There's only one triple here, so we need to check one triple. Is that triple active or inactive? Well, we can look at our categorization. Our categorization shows that this kind of triple, V structure, with no evidence observed in the bottom of the V structure or anywhere below, is inactive. So this is an inactive triple. That means this triple ensures that along this path, there can be no influence from R to B. This is the only path. So the only path between R and B is not able to carry any influence between R and B. That means that R and B are independent. Next one. How about R independent of B given T? Okay, there's some evidence. So first thing we do, we kind of shade the evidence node. Then we look at all the paths between R and B. Still only one path. This is the one path. That one path is only one triple long. We look at that triple. Is this triple active or inactive? Well, it's a V structure, but there's evidence observed in the bottom of the V structure. We know in those scenarios that influence can run through that triple. That triple constitutes the entire path from R to B. So that means influence can run in the entire path because it's only one triple long and that one triple is active. So there can be influence all the way from R to B, given T. So we cannot claim this conditional independence to be true. So can't claim anything about conditional independence here. How about R and B given T prime, which lives at the bottom here? Well, let's go through the same procedure again. It's actually very mechanical and fairly straightforward. We look at all paths from R to B. Only one path. We look at the triples along the path. Only one triple. That one triple here, is this triple active or inactive? Well, this kind of structure, activity depends on whether there is evidence at the bottom or below the bottom. Indeed, there is evidence below here. So this triple is active. This active triple constitutes the entire path. So the entire path is active. If we have an active path from R to B, then we cannot claim conditional independence. So no claim of conditional independence there. Next one. Slightly bigger network. How about, is L independent of T prime given T? So how do we do this? Given T, so we'll shade the T variable. We're concerned with L and T prime. The only path connecting them is this path over here. This path has multiple triples along it. Here is a first triple. And this is important. The second triple starts here, runs this way. So you can see there's a lot of overlap when we pick all triples along a path. Here, there's two triples along the path. We want to check, is this path active? Okay, let's check the first triple, the one up here, it's a causal chain, L to R to T. Causal chain with no evidence in the middle, so it's active. So first triple is active. How about the second triple? Is that one active? It's also a causal chain, but a causal chain with evidence in the middle. Causal chain with evidence in the middle is inactive triple, so this one is inactive. If we have a path consisting of multiple triples, if any single one of them is inactive, that means that one blocks the flow of influence, and so then the path becomes inactive. So this path is inactive. It's the only path between L and T prime. The only path between L and T prime is inactive. That means L and T prime are independent, conditioned on T. Next one, L and B. For L and B, let's have you take, let's say, a minute, talk with your neighbor, and think through whether or not we can claim independence of L and B given this basenet structure. Okay, let's see. Who thinks, yes, we can claim this independence? Raise your hands. A bunch of people. Okay. Yeah, over there. Kara, why?
Because you're not given any information, but then also you have that none of them are inactive.
Okay, so the reasoning here was that there is no evidence along the path, and these are triples that when there's no evidence, they might or might not be active. I think we need to go in a little more detail than just repeating what you just said. So let's step through this in detail. L and B, no evidence. This is the only path between L and B. How many triples along the path? There's a triple here and another triple here. Look at the first triple here. It's a causal chain. The middle node is not observed, so this one is active. Second one is a V structure. There's no evidence in the V structure, so this is inactive. Once you have one inactive triple along a path, the path becomes inactive, and we have, this is the only path. The only path is inactive. Oh, what's going on here? Only path is inactive, so that means we have conditional independence of L and B given zero evidence. So yes, most of you were correct. We have conditional independence here. Now, one thing you can do, if we think about this one again, we have L and B we care about. And I said, well, this is the only path, and we have a bunch of triples. The slightly faster way to get through it than what I just did is if you can directly identify the triple that's inactive. So you say, instead of linearly going through all the triples, if you say, oh, I know that this triple is inactive, I don't have to check any other triples, because I already found one that is inactive, which will break the influence in that path, and we now know this is an inactive path, and we're done with checking this path. Next one, is L independent of B given T? Well, this is the same reasoning as we just went through. We're looking at L and B, but now this one here is observed. This triple before was the inactive one. blocking things. Now, thanks to the evidence here, this is now an active triple. So this triple is active now. The other triple along the path is also active. So the entire path is active, and we cannot claim any conditional independence. What if we, instead of T, observe T prime? Does that change anything? No, it doesn't, right? Because the triples between L and B remain the same, and whether this triple here is active or not only depends on whether there is anywhere along from there down any evidence. It doesn't need to be in T, it can be in T prime, all has the same effect. So also here, we have a path that is active, so we cannot claim conditional independence. How about this one? We are still looking at L and B. We observe R, and we observe T. Who believes we have conditional independence here? A few people? Why? Okay, so the answer was we have only one path. Along that path, we're able to find an inactive triplet, namely LRT, sitting over here. Once we find an inactive triplet, we know the entire path is inactive, and at that point, if that's the only path, we can claim conditional independence. So yes. Here's another example. In this one, sometimes there's more than one path between nodes. Stories could be raining, which could cause traffic, which could also cause maybe independently the roof to drip or not, and then you could be sad either because the roof is dripping or because there is traffic. Okay, questions. Is T independent of D? Let's have you think about this for about 30 seconds, talk with your neighbor, and see what you come up with. Who thinks we can claim independence of T and D for this base net? Not a lot of you. That's great. We can't. Why not? T and D. To check if we can claim independence, we have to check all paths. And if we find a path that is active, then we cannot claim independence. Well, the path along the top here has a single triplet. That triplet is an active triplet, so we have a path of influence, so we cannot claim independence. You might wonder, how about this bottom path over here? Well, that one is inactive. So what we have here is a situation where there's two types of paths, active and inactive paths, but once there's a single active path, it voids our ability to claim independence. So we can't claim it. How about once we condition on R? Well, now there's all of a sudden independence, because the bottom path was already an inactive triplet, and now the top path has gotten blocked, also inactive, both paths inactive, so we have independence. How about if now we also condition on S? So we condition on R and S. What happens? Well, conditioning on S will activate the path along the bottom. Once that's activated, there's an active path, and we cannot claim independence. Okay, now let's go back to the question that came right after the break. Why and how might we investigate all independencies, and what do we do with this? So, given a Bayes-net structure, we now have an algorithm called deseparation, which we step through in our heads and on the slides, but in principle you can code in a computer program. You could write a computer program that, given a Bayes-net structure, in the graph finds all the paths, along each path, checks the triplets, and then checks whether or not each triplet is active, and then based on that decides whether or not there exists an active path. And if there is an active path, then it says cannot claim anything. If there's no active path, it says independence. So we can do that programmatically now. What can we do with this? What it actually does, the list that we can generate this way, if we try to look at all of them, is a list of assumptions we make by choosing a specific basenet structure. So let's try to do this. Here is a few basenet structures. Let's compute all the independencies that we can claim for each of those basenet structures. How about the first one? Y common cause to X and Z. What independencies are present there? Only one. It's X independent of Z given Y. How about the next one? Causal chain. X to Y to Z. What are the independencies? Also only one. In this case, it's X independent of Z given Y. Actually, same one as before. They have the same independence. And it's the only independence you can claim based on this structure. How about the next one? X and Z point into Y. What are the independencies that we know? Well, when there's no evidence, X and Z are independent, and that's it. How about the last one, where we have Z to Y, and then Y and Z together to X? What independences do we have here? None. Why none? Because every node has all the previous nodes in the ordering as its parents. That means we can have an equation for this basenet that matches with the chain rule, and we made no assumptions. So here we have the empty set. So one interesting thing already comes up here. If you look at these two basenets, they actually end up with the same set of independences. What that means is that if you want to represent a distribution over three variables, x, y, and z, that represents something in the real world, whether you use the first one or the second one, you'll be equally capable of capturing that distribution. If somebody represents it with the first one, you can turn that into a new basenet structured like the second one that represents the exact same distribution. Because the assumptions you make by using the structure is the same, and so they can represent the same distributions. On the other hand, if somebody gives you a distribution represented by the bottom basenet over here, that basenet makes no assumptions, so it's very unlikely that if you get a distribution represented by this basenet here, that you can then represent it by any of the other basenets, because the other basenets make assumptions, independence assumptions, and if they're not holding true in the distribution you're given, then you cannot capture that distribution. So you might wonder, why do we even have both versions if they can represent the same distributions anyway? Sometimes it's easier to specify one than the other. If the way the world works is really something along the lines of y tends to cause x and z, then the probabilities in the table of this basenet will be much, much easier to come up with than if you then represent it with some chain basenet. Similarly, if the effects are really a chaining effect, then it's going to be much easier to use the second basenet to represent that probability distribution than the first one. You still could use the first one. They are interchangeable, mathematically speaking. In terms of practical ability to come up with the numbers in the CPTs, it might still matter which one you pick. So, taking a further step back, let's look at distributions over three variables. And you can think of a distribution as, let's say, a point in this space here. And so this space here is any point corresponds to a distribution. Now we can say, if we look at distributions that can be represented by this basenet over here, x, y, and z, zero connections. So all independencies that you can possibly come up with between three variables, they all hold true. You can represent only a very small set of distributions with this kind of basenet, and that's this kind of small green thing in the middle here, where a different point in that set corresponds to a different distribution. Like maybe one distribution has probably 1/2, 1/2, 1/2 for each of x, y, and z. Another one might be, a biased coin flip for x, maybe 0.9, 0.1, and y and z still have 0.5 and 0.5. Yet another one could be x 0.9, 0.1, y 0.8, 0.2, z 0.2, 0.8. So any such choices will be representable by this base net here and live in that small set. Now, if you take a different base net structure, the one shown here, what do you get? For any one of those three, you get the same conditional independence assumption, only one, that one. X independent of z given y. That is a lot less assumptions than you made over here. So it's a larger set of distributions that you can represent if you're only forced to make this one assumption rather than being forced to make a lot of assumptions. And it's also the same distributions. Any distribution represented by the first one, you can reformulate as represented by the second one or the third one. It's interchangeable from a mathematical point of view, even if from a practical point of view, you often will still prefer one structure over another one. Here, how about these base nets? These are all base nets that make zero assumptions. So if you use any of these base net structures, you're not forced to make any assumptions, and you can represent any distribution over the three variables. How come there is 6 of them? It corresponds to the 6 possible ways of ordering those variables. It's like the chain rule. We have 3 variables, so we first have 3 choices, which one to go first, then 2 choices left for who goes next. So 3 times 2, 6 choices of ordering, and that corresponds to, each of these corresponds to one of the 6 orderings in the chain rule and in constructing the base net. Again, if somebody gives you a distribution, for example, represented by this base net over here, and you wonder, can I instead use maybe this other base net? The answer is yes, they're equivalent. These structures make the same assumptions, namely no assumptions. But if somebody gives you a base net like this, and then says, can you please give it to me in that form factor? Usually that's not going to work. There might be some coincidence where some very specific choice of the conditional probability tables makes it still work out, that there was like a hidden independence assumption that was just there because of the numbers, but typically it won't work out because here you need an assumption to be able to use any of these structures. And so going back to the earlier question, this is kind of what you think about when you build models. You think about what assumptions am I making, what's the entire set of assumptions I'm making when I choose a base net structure, and also how can I structure my base net in a way that it's easier to come up with conditional probability tables for it. And so even if you say this is the only assumption I'm going to make, you might still say, well, among the choices I have available, maybe the first one is the one that makes it easier to think about what is really going on here. Any questions about this? Yes?
We don't see any models that shape like these.
Okay. Yeah. So the question is, how about a model maybe that looks like this? Y. Oh. X. Z. So what are the conditional independencies here? Just X independent of Z, nothing else. So maybe if we had purple or something, we could have another set of models. What would happen now if we want to draw this on here? This one here, purple, makes less assumptions than the green one. So everything that lives in the green set, purple can handle. That base net can do it. Now, if it really lives in the green set, it would be kind of a very non-communicative choice of base net structure to use this one with 2 edges in it if you could have gotten away with 0 edges. But you can do it. You can represent. So everything in green can go in, will be subsumed in purple. How about everything in red? Well, this is kind of a different assumption here. These assumptions are not directly comparable. X independent of Z versus X independent of Z given Y. So what's going to happen here is that you're going to have a purple set that, let me just color it in. It will have all the green included. Not this thing here. So all the green it'll have. And then, just like the red one encompasses the green, but not everything, because it still makes an assumption, there would be something similar, but we wouldn't want it to overlap with the red one, so it's kind of hard to draw, but let's say we kind of sliced off, we stopped the red one over here and over here, then the purple one could kind of come out of here and maybe run here. Something like that. And there will be others, because you could reorder the variables. Instead of y at the bottom, you could put z at the bottom or x at the bottom, and same thing for these red ones. You could put not y in the middle, but put x or z in the middle, and then you'll have similarly other things coming out. A little hard to draw, but it will have the same kind of effect where they'll capture the green, but they will have non-overlap otherwise with the other ones. Let's see. And then the blue one will always have them all included, because the blue one makes no assumptions, so it can capture everything any basenet with less edges can represent. Essentially, whenever you remove an edge, you make an assumption. When you have all the edges, you've made no assumptions. Any other questions about this? Okay, so quick summary. Basenets compactly encode joint distributions. And the reason we care about that is because we want to reason about large numbers of random variables, hundreds, maybe thousands or millions of random variables to do complicated things. And encoding the joint distribution directly is not going to be practical. By using a basenet, we introduce some guaranteed independencies that we can read off directly from the graph structure. The algorithm we saw today, d-separation, gives us a way to methodologically check independencies. If you then run it for all sets of variables, you get the full listing of all independencies that characterize what you assume when using a specific basenet structure. Last bullet point here. This one's a little subtle, but it is possible to have independencies that your d-separation algorithm does not find. What I mean with that is that d-separation will only find the independencies that are true no matter what numbers you put in the conditional probability tables. That's what it does. But if you put in very special numbers in the tables, there might be additional independencies that you cannot read off from your graph structure, such as if you put 1/2 everywhere, then there will be complete independence, and you won't be able to read that off from your graph structure because the graph structure doesn't tell you there's 1/2 everywhere. It just shows you the structure of the basenet. Where does that put us? Last lecture, we covered representation. Now we covered better understanding what assumptions we make when using this representation. Next lecture will be probabilistic inference, exact. Then the next lecture will be, to do it exactly might still be incomplete in some scenarios, so we might need something approximate through sampling. And then after that, we'll start looking at learning the basenets from data. Okay, that's it for today.